So, what if you had a solution that has an acid and its conjugate base present? So, when we looked at salt solutions in the last module, I told you you don't have to worry about calculating the pH for a solution that has a salt where the cation could be acidic and the anion could be basic. However, when the cation and anion are a conjugate acid base pair, we get a special type of solution that you can calculate the pH of without having to do all of the tests that we did. So when you have an acid with its conjugate base or a base with its conjugate acid, well, if it's a weak acid or a weak base, you can have a solution that behaves like a buffer. So what I'm going to do first is set up this calculation. It's going to be the pH of a solution that has an acid and its conjugate base both present, but I'm going to solve it using equilibrium setups. So everything that we have known and done so far. Now, you do not need to use this method going forward. I'm going to give you a shortcut equation, but I want you to see where everything is coming from. So the solution that we're going to do will be 0.25 molar nitrous acid and 0.25 molar sodium nitrate. So in Ka versus Kb, now I'm doing the acid and its own conjugate base. So these two things are related to each other through Kw. But out of the two, the Ka is bigger, so the acid is stronger. So I'm going to write the acid behaving like an acid as my reaction for my rice table. So it's nitrous acid in equilibrium with nitrite and H+. However, the nitrite will come in when I do my initial row. So in my initial row, I will have 0.25 molar of the HNO2 and 0.25 molar of the NO2 minus, 0 H+. And then I have 0 for my products. My reaction has to go forward, fill in my equilibrium row, set the equilibrium row equal to Ka, solve for X, which is the same as my H+ concentration. And if I take the negative log of that, I get a pH of 3.34. So this is what is called a buffer solution. You can treat this like an equilibrium, but like I said, we're going to get into some easier to apply versions of this. So a buffer solution is special, and the characteristics of it are that it contains similar amounts of a weak acid and its conjugate base, or a weak base and its conjugate acid. We call it a buffer solution because it resists changes in pH. So it will stay approximately the same pH. So it will have something so that you could add acid or add base to the solution and it would like buffer against that change. In the solution, in the buffer solution, if you add base, there is a weak acid there to neutralize it. And if you add acid, there is a weak base there to neutralize it. And the thing that is important about it being the conjugate pair, if you take a weak acid and react it with a base, the product is the conjugate base of the weak acid. So whenever you react one buffer component, you generate the other component as the product. Because of the common ion effect, which is just another way of saying Le Chatelier's principle, similar to the way that we talked about Le Chatelier's principle with polyprotic acids, the pH of a buffer solution will be less acidic or less basic than what you would expect from the pure acid or the pure base. All right, so what I have next is just a rewriting, highlighting the NO2 minus on each side, showing that we have the acid and we have the conjugate base present in this solution. So let's see how this works as a buffer. You can poke the system and see what happens. Now I'm going to continue with this equilibrium treatment, but once we have an equation that works just for buffers, that equation will be more straightforward. So my reaction is still the same, and I've filled in my equilibrium row. So based on the X that I calculated, which is filled in for H plus, how much HNO2 and how much NO2 minus would I now have? I have these amounts, right? You can see that my NO2 minus went up by the amount that my HNO2 went down. And what I'm going to do to poke this system is add some acid. I'm going to add 0.01 moles of H3O plus. And I've got that here. This is like the perturbation that I'm going to do. I mean, let's say it's like 0.01 molar since we're working in concentrations in our ice table. So I'm going to add that to the H plus. Now you can predict what would happen here. Because this is an equilibrium, we're doing a perturbation, it's adding product, it should shift to the left. But, right, we could go through all of the steps to figure this out. I've got a new initial row after adding that 0.01 molar of the H plus. So now if I calculated Q, it would tell me that this is going to move to the left. And I show that with a plus X in the reactant and minus X's in the products. So at equilibrium, I have these plus X and minus X values. This is how much my system would shift after this one perturbation. If you go through and calculate what X is, you get an X value of 0.00996. So, right, that X, that's how much it changed. So my question to you is, how does this compare to what we added? Well, we added 0.01 and then it used up 0.01 if you round up. So it's nearly 100% of the acid that was added got used up by the buffer. So we put in 0.01, it used up almost 0.01. It kind of absorbed the acid that we added. So the question is, what's the pH, right? We've said that buffers buffer against a change in pH. So with my new equilibrium values, I would get a pH of 3.3, which is pretty small. So the pH started at 3.34. We added 0.01 molar acid, and our pH only went to 3.3. That's really quite good. Now, what if there was an easier way to solve? Here's one easier way to solve. It's still an equilibrium table, so there's an even easier one after this. But one easier way to solve is to have everything at the beginning. So let's say that our problem is that we have 0.25 molar HNO2 and 0.25 molar NaNO2, and we are going to add 0.01 moles of H3O plus to it. You can assume, we're adding acid, you can assume that the added acid completely reacts with the base, and then start from that point to calculate the equilibrium. So instead of finding the equilibrium values for the buffer and then adjusting from there, we're going to adjust our initial values. So we're going to say I initially have 0.25 molar HNO2 and 0.25 molar NO2 minus, 0 H plus. I'm going to add 0.01 H plus. When I add acid, the base reacts with it. So I'm putting this H plus in here, and then I'm immediately going to react it to get a new set of initial conditions. The base is what reacts with the acid. So I will use up the same number of moles of the base, which is the NO2 minus. So I'm going to subtract 0.01 from the NO2 minus. And when I do that, I will make 0.01 of the HNO2. So my starting conditions are that I have 0.26 of the acid and 0.24 of the base, and 0 of the H plus, because the acid that I added was used up by reacting with the base. And then I could go to equilibrium from here. And you can try this out. You should get the same answer with a pH of 3.3. The even easier way to do it is with something called the Henderson-Hasselbalch equation. So Henderson-Hasselbalch works only for buffers. It is pH equals pKa plus the log of the initial base concentration divided by the initial acid concentration. This only works when you can assume that X is small. However, that's good enough. The buffers that we use are all going to fit into this category. You will be able to use Henderson-Hasselbalch for every buffer that you encounter. So the nice thing is that Henderson-Hasselbalch, you can use it for acidic and basic buffers. You're still using Ka though, so the equation itself does not change. It's pH and pKa and the log of the base divided by the acid. What that means is that if you had a buffer that had ammonia and ammonium, you still need the Ka, and the Ka will be for ammonium because it is the acid. So you will have to take the Kb of ammonia, calculate the Ka of ammonium, and then take the pKa for ammonium to put into the equation. You'll also see some questions that ask you to design a buffer. When they ask you to design a buffer, what they're looking for is your ability to think about this Henderson-Hasselbalch equation. So what they are asking you to do is to choose a weak acid that has a pKa close to the desired pH of your buffer, right? Because your buffer pH is the pKa, and then you adjust it with that acid and base ratio. So you want to start with something that has a pKa that's really close to that pH. You can then adjust, right? You can use a little more base or a little more acid to tailor that pH, but the most that you can do is really within 1 pH unit, which remember, it's a log scale, so like 1 pH unit is a lot. Relatively speaking, it's a factor of 10. So for example, if my pKa were 5, I could make a buffer solution with pH values between 4 and 6 using that weak acid and its conjugate base. All right, so let's use Henderson-Hasselbalch to do this calculation of our nitrous acid nitrite buffer. So calculate the pH of a buffer with 0.25 molar nitrous acid and 0.25 molar sodium nitrite. The pH is the negative log of the Ka. I can just get the Ka. I don't have to determine if it's stronger or not. Plus the log of the base concentration initially over the acid concentration initially, which is 0.25 over 0.25. So the negative log of the Ka is 3.34. And then the log of 1, because my concentrations are equal, is 0. So the pH of this buffer is 3.34, which is what we found from the equilibrium table, but I was able to do this with just one equation. So please use the Henderson-Hasselbalch equation for buffer calculations. You don't have to set up an equilibrium table. This will work great. All right, so quantifying buffer capacity, we've kind of already said this, but just like to put some things out here so that you have the information. One, a more concentrated buffer can react with more acid or base than a less concentrated buffer. Right, concentration is just the number of moles in the volume. So if you have more moles in that volume, you can react with more things. This just means like, so we had an example with 0.25 molar each of the acid and the conjugate base. If you had 1 molar each of the acid and the conjugate base, you would be able to put more just objectively more of the acid or base into that buffer to get a reaction. It's the ratio that also affects it, and it's related to the effectiveness of the buffer. So the buffer is most effective when its pH is within 1 unit of its pKa. If you go too far beyond 1 unit, then suddenly it's not really a buffer, because you could add maybe acid or base to neutralize like whichever thing there is more of. Um, but it won't buffer against both, because you'll have either a lot more acid or a lot more base if you are outside of this 1 unit of the pKa.